Hi, we are team number 7 Burj Arab. 오정훈 is team leader and sub-presenter at this weekend. 공태원 is PPT designer and study DMD. 유성우 is video director consist episode. 박철임 is main projector and study DMD. Lastly, Mungujin is PPT planner research and study DMD. This week, we studied DMD to control the Burj Arab vortex shading. We will briefly review the contents of last week and introduce the contents of this week. We looked at how bad windows are at skyscrapers last week. Architect Tom Wright and structural engineer Anthony McCarter began the design of the exoskeleton that was outwardly beautiful and structurally stable to withstand wind loads. A structure consisting of only horizontal and vertical members is easily rotated and consequently destroyed in direction of force, because it cannot resist the moment at pin fixation. Therefore, additional structures were needed to reinforce them. The structure is truss. Truss is a triangular structure that forms additional tensile and compressive stresses on the structure, further stabilizing the structure. The structure is 85 meters long and weighs 165 tons, with 3 on each side. Inside, there are 8 small triangular structures, and the pins on both sides are made for excellent construction. The spiral truss structure was made at a welding station about 15 kilometers from the Burj Arab, because it was not a situation where it could be assembled into several parts. The transfer was prepared with the complete structure. Building contractors bring in one of the world's largest heavy lift transporters, a beast with a total of 80 wheels. It makes the slow journey to the construction site of an average speed around 6 km per hour. Through this process, they prepared to complete the perfect exoskeleton. If a perfectly designed steel structure to resist wind loads fails to the work in combination with the building, it will be the same as a statue erected in front of the building. The combination of exoskeleton and building is so important. The exoskeleton of the Burj Arab and combination of building can be divided into main parts. A combination of building and exoskeleton and a combination of exoskeleton and spiral truss. For the first connecting parts, rear bracing and exoskeleton, the exoskeleton was connected in a straight line with 3 girders of rear bracing frame to deliver the lateral load on the building to exoskeleton. Second, for core and exoskeleton connections, the exoskeleton was completely connected to the core from the start of construction. Then, a cable holding 225 tons was attached to both ends of the truss, and 2 giant wheels raised the spiral truss to the connecting position. At this time, the truss was raised to the angle calculated in advance, so that it could be properly fastened to the pin. This is an image modeled using Revit of concrete core, exoskeleton, and spiral truss of Burj Arab.
Now let's move on to this week's episode. As discussed earlier, architect Tom Wright and the structural engineer Anthony McCarter were able to complete a stable steel structure to resist wind loads. Thus, Burj Al Arab was becoming the world's best hotel with its stability and beautifulness. All seemed to have been solved when the wind load, which was the problem of skyscrapers, was resolved. But a new problem arose. The problem was suggested by aerodynamicist Volker Boutgrate. Burj Al Arab was being built in an unusual location with unusual exterior, different from a typical square-shaped building. For this reason, there was a risk of vortex-induced vibration. Vortex vibrations are a problem that should always be considered in windy areas. An example of a hazard caused by vortex vibrations is the Ferry Bridge cooling towers in England. On the 1st of November in 1965, 3 out of the original 8 cooling towers collapsed due to vibrations in 85 miles per hour winds. The vibration was caused by the vortex between the towers. As such, the destruction of structures by vortex is very critical. Then, how did Burj Al Arab handle this problem? When the wind acts perpendicularly to the structure, the separation of the airflow occurs on the rear of the structure, causing vortex jetting. Vortex is created and dissipated periodically, causing periodic force, vortex-induced vibration to the structure perpendicularly. This vortex vibration creates a repeated force to the structure, causing various problems. Especially as Burj Al Arab was built in the shore of Arabian Gulf, it was easily exposed to waves, winds, tidal currents. The exoskeleton and spiral truss could resist wind load, but not the vortex jetting. Therefore, aerodynamicists executed wind tunnel tests of Burj Al Arab. Before Burj Al Arab, most of the buildings in the Gulf were fairly orthodox shape. They were square, they were rectangular, they were nowhere near this scale. So doing the wind tunnel test for the building in those days in the Gulf was almost outrageous. But for this extraordinary structure, it was essential. The wind tunnel simulates the wind effects of the Gulf around 150 scale model. Certain wind conditions blowing over sharp edges on the steel structure created miniature tornadoes which could result in dangerous vibrations causing the building to destruct. By this wind tunnel test, the aerodynamicists searched for a way to handle this vortex vibration. To solve this, the engineers decided to use tuned mass damper, TMD in short, a vibration energy attenuator. TMDs operate on a principle that reduces vibration by absorbing the transferred energy applied to the structure to ensure the dynamic stability of the structure. These TMDs with additional 5 tons weights are installed at vulnerable points in the exoskeleton. When the wind blows and vortex shedding starts to create dangerous vibrations, the 5-ton weight will swing instead of the structure and damp down the vibrations to well within safety limits. 11 of these systems are fitted from the top of the 60 meters mast all the way down through each of the steel bow structures. These dampers safely canceled out the threat. For the past 3 weeks, we've looked upon 3 structures that resist wind load: exoskeleton, truss, and TMD. Exoskeleton consisted of rear leg and rear brace frame. The truss was created in a spiral form and extra 8 trusses supported one big truss. Lastly, TMDs were applied for more stability in 11 parts of the building. In the end, all these structures for stability could fit fluently to the whole building without going against the architect's initial design to create an icon of Dubai. With its stability guaranteed, next week we'll look upon the most luxurious places in Burj Al Arab, the Sky Restaurant, and the helipad, and what challenges were there. Thank you for listening.